Yes, so the next talk will be given by Vadim Zaliva, who will tell us about the CHERI C memory model. Please.
Hello, my name is Vadim Zaliva. I will be talking about my joint work with my collaborators on CHERI C memory model for verifying temporal safety. So this is how this work was funded. So the goal of this work was to define a memory model for CHERI C, which is a critical component for understanding CHERI C semantics and providing framework for reasoning about security properties. Our memory model has three key components, distinguishing components. First is CHERI-specific pointer provenance tracking scheme, PNVI CHERI, a revocation mechanism to ensure temporal safety, and finally the formal proof of temporal safety of the proposed memory model. Quite a few words here: pointer provenance, memory safety, CHERI. Some of you might be familiar with them, but to bring everybody up to speed, let's start with some background. First, what is CHERI? Memory safety bugs are the major source of security vulnerabilities. And CHERI was one of the answers to that. It is a capability-based hardware architecture extending conventional ISAs to enable fine-grained memory protection. It was developed by University of Cambridge and SRI. And most notable hardware implementation is Arm Morello chip, which is based on ARM64 design and is currently available as an evaluation board from Arm. It is a mature platform with more than 30 million lines of code ported to it, which includes FreeBSD, kernel on user space, Qt, KDE, Postgres, NGIX, WebKit, and many more. There are several studies which analyzes the impact of CHERI on the security, and they show significant reduction of the number of vulnerabilities. So 30 to 70% for Microsoft Security Response Center, 56% of FreeBSD kernel vulnerabilities over past 22 years, and 73% in the open source desktop stack, which is Qt-based, KDE-based. Presently, CHERI C and C++ are the most mature high-level languages for writing code targeting hardware. CHERI C is a dialect of C programming languages developed as a C-lang LLVM C compiler fork. It is originally defined by CHERI C++ programming guide, and there is proposed formal semantic in COG and in English prose. There are two other CHERI C compilers exist. One is GCC, and second is CHERIoT LLVM. Across these three compilers, the three supported architectures are Arm Morello, CHERI-RISC-V, and CHERIoT. CHERIoT is from Microsoft. It's also RISC-V based, targeting mostly mobile embedded devices. So the idea of the CHERI C is we represent the pointers as a capabilities. On the left side, you see traditional pointers, how you might see them on the existing architecture. For example, 64-bit architecture like ARM64. The pointers are just 64-bit virtual address in memory. So they implemented as an integers. They could be created from integers, cast back from integers to the, but you can cast between pointers and integers, and you can manipulate them for the integer arithmetic. They lack any integrity protection, and they do not prevent inappropriate use. On the right side, you see the pointer in CHERI C. It's a capability. And capability in CHERI is 129 bits. It's 64-bit virtual address as before, with some additional meta information, some additional fields. Most important ones are bounds, which control what part of the memory you can access through this pointer. And the second important field is permissions, which governs what kind of access you're allowed. Is it read, write, or execution? And additionally, there's validity tag, which guards the integrity protection. And you couldn't just fake the capability. You couldn't just modify it arbitrarily. You have to derive them in a special way, preserving some certain security properties. And all of that is enforced by the hardware, and it's reasonably efficient. Next concept to introduce is a pointer provenance. And you might think that compilers think about pointers as an integers, but this is not true, even not for CHERI. Consider the following example. If variable x and y in line 1 allocated in adjacent memory regions, the pointer p and q will have exactly the same bit representation. They have exactly the same value. However, depending on the compiler's decision of whether p and q could alias, the optimization could lead to the different observable behaviors as shown above. So GCC optimizer decides that they do not alias, and the initial value of y equals 2 can be propagated to the final printf, and that's what it prints. C-lang, on the other hand, more conservatively chooses not to propagate the value. So morally, the pointer p points to the, initially derived from the pointer to the object x, and point 1 pass object x. That's how we can think about it informally. And pointer q points to the first byte of the next object pointer y. So this is a notion. This is this notion. So that's exactly what this pointer provenance is. It allows you to allow the C abstract machine to track the region of the pointer, and this information can be used to justify the soundness of compiler optimization that based on alias analysis. There have been several proposals for the pointer provenance. The more mature ones is called PNVA-AEDI, which is now submitted as a draft of ISO technical specification. So hopefully it will make it into the standard eventually. PNVA-AEDI means pointer not via integer, address exposure, user disambiguation. I would not decheaper all that. You can read the standard if you propose specification if you're interested further. Previously proposed CHERI C semantics uses PNVA-AEDI scheme. And if you apply that to example before, it will tell you that the P is a pointer derived from the address of object X. And now it's pointing one past of the footprint of this object. So dereferencing this pointer, using it is indeed undefined behavior. So PNVA-AEDI clarify these questions disambiguate this situation. But CHERI hardware bounds will also prevent this right. And there is apparently there is an overlap between PNVA-AEDI and CHERI. More about that later. Next concept is a temporal safety. So temporal safety ensures that objects in memory are accessed only within their intended lifetimes. In particular, two undesirable scenarios are usually considered. Use after free is an object was freed, but the memory is accessed before the underlying address space had been reused. And use after reallocation is when the object was also freed, but the memory is accessed after the underlying address space had been reused. So the difference is between the first case, you have a dangling pointer pointing to some free memory, a stale pointer, and in the second case, it can end up pointing to some live object allocated in the same space. So security implications are different between these two scenarios. However, from point of view of ISO C, all instances of use after free and use after reallocate refer to an object outside of lifetime and is undefined behavior according to the standard. However, in the presence of undefined behaviors, compilers may generate the code which attempts such illegal accesses. Unfortunately, default CHERI protections only ensure spatial safety and will not prevent this. To mitigate temporal safety violations, the revocation mechanism is used. Revocation works by invalidating stale pointers to deallocate memory. In CHERI, pointers could be revoked by just clearing the tag bit, so it's a relatively easy, lightweight operation. But if you think about it, if you have to, each time you deallocate the object, you have to swipe all the memory, find all the pointers, and invalidate it. So it's from performance of view, there will be a penalty. Even though there are some hardware mechanisms to speed this up slightly, but usually it's staged and the sweeping revocation is used. And sweeping revocation quarantines the freed memory and then periodically sweeps and revoke the pointers to it. So in this scheme, each allocation could be in one of three states. It could be a live allocation, which has just been allocated, and it's currently in use by the program. It could be a quarantine. It's an intermediate state that the memory is still retained, and you still have a pointer pointing to it, which haven't been revoked yet. But because it's in the quarantine, this memory space will not be yet reused by reallocator, so no new objects can appear there. There are several attempts to address heap temporal safety for CHERI in C and C++. CHERIoT, cornucopia, and cornucopia reloaded, to name a few, and all of them using various sweeping revocation implementations. If you look at the memory as a whole in presence revocation, it could be in one of the two states. In the clean states, the quarantine is empty, and there is no pointers pointing to non-live memory. In the dirty state, some memory is in quarantine, so there might be still dangling pointers pointing to the quarantine memory. So we start in the clean state. Each time you deallocate the object, you call free functions and see it's traversed to the dirty state. And it stays there until the revocation pass run. And then the revocation pass run, it revokes all the pointers, cleans the quarantine, and it returns back to the clean state. So now I think we have sufficient background again to revisit our contributions, what we've done here. So we examined the relation between the pointer provenance and CHERI and proposed streamlined CHERI-specific pointer provenance tracking scheme, PNVI CHERI. We defined in COG a specialized object memory model tailored for CHERI C. This model uses PNVI CHERI and includes support for generalized version of 5 existing CHERI capability revocation mechanisms. We integrated our model into existing executable CHERI C semantics and tested it against existing CHERI C semantics test suite. And finally, we formally defined and proven in COG temporal security guarantees provided by this memory model. So memory model offers an interface to dynamic memory allocation, release, and standard library functions like memCPU, memCMP. Also, it offers interface to memory operations, reading and writing, and pointer actions, arithmetic, pointer comparison, alignment, and conversion. Our memory model is integrated into Cerberus. Cerberus is executable ISO C11 semantics, originally developed by Kayvan Memarian at Cambridge. It is a concrete memory model, which means it uses integer addressable memory space. And it also keeps tracks of whether memory at given address was initialized. So it deals with initialized memory as well. Originally, the implementation was forked from the Cerberus C11 concrete memory model, which used PNVA AUDI. But the original model was written on a Campbell. Because we wanted to prove things about that, we rewrote it in COG. We also replaced PNVA AUDI with PNVI CHERI, and we added support for revocation. So that's how it's significantly different from the previous one. Speaking about memory model, it will be useful to contrast it to the memory model of CompCert compiler many of you are probably familiar with. So in the CompCert compiler, the pointers are pairs. It's simplified, obviously. It's tuples, pairs of a block ID and offset within this block. Within the CompCert semantics, each object is allocated as a distinct block. And whatever pointer arithmetic you can do, you can just change the offset within this block. It could never span and could never jump to the next object. So this is a very convenient scheme from semantics point of view, because you have this explicit relationship between the pointers and memory allocations, which are one-to-one to objects. This is what we called provenance before. So this is explicitly available in the CompCert. But this memory model of CompCert makes some things more difficult. For example, it's more difficult to express and reason about pointer arithmetics, or, for example, pointer bit manipulation and pointer to integer cast. Although there's some research extending it for that capabilities. In CHERI C, the pointer is a capability. And I just showed the two fields which we care about, the address and bounds. So the address is references directly to the table of the abstract bytes. And the address is just integer, so you can easily do pointer arithmetics on it. Additionally, memory model keeps the list, the table of the life and quarantine allocations, address by unique ID, and they have quarantine flag, starting address, and lengths. So as you see in this memory model, there is no direct provenance relationship between the pointers and allocations. And in implementation like PNVA AUDI, it was kept by maintaining additional fields in the pointers in the semantics, which are not present in the runtime. These ghost fields. So more formally, the memory state of the CHERI C memory model I showed before is shown here. That's the definition we use in COG. So we already looked at the alloc map, allocation, and byte map. Another interesting one is a cap map. Cap map is a table which, for each capability aligned address, it keeps some meta information. The most important is the validity tag. So validity tags for capabilities, they're not stored in the main memory. So when you store the capability in memory, you're storing 128 bits, not 129. And this bit is maintained separately. And this is also how it happens to be implemented in the hardware, like in Morello chip. It's not part of the main addressable memory. It's maintained by the system, and you could not directly manipulate this bit. You can do it through a special instruction, and this bit automatically cleared if the integrity of capability is compromised. So that repeats that. And there's additional couple of fields about the watermarks for the allocation IDs and addresses. So the key idea of the PNVI CHERI is that instead of associating additional meta information with pointer objects to track their provenance, it uses runtime capability fields to unambiguously recover their provenance. Getting back to our picture from the previous slides about the relationship between the capabilities and the allocation map on the left, people when usually they talk about the capability, they think provenance, they think that the provenance between the addresses and the allocations. In fact, it's a relation between the pointers and allocations, and the pointer in CHERI is more than that. And it happens that the bounds field is what we can use to calculate this provenance relationship. The idea is, what makes it possible is monotonicity property of CHERI capability derivation. It works in the following way. When you allocate the object first, the allocator returns the capability, which have a bounds matching exactly the footprint of the allocation. And any pointers to this allocation will have to be derived from this pointer. You couldn't make them from out of the thin air. You can only derive from this pointer. But the derivation mechanism in CHERI, for security reasons, it only allows you to narrow the bounds of the derived capabilities. You could never extend it. So that means when you're deriving the pointers to allocation from some initial pointer, their bounds will never exceed the bounds of the original allocation. And that's intuition which gives us a way to recover the provenance. So if you have a capability, you have to just look for the lower bound that's sufficient for the matching record in the allocation map, which encloses the lower bound of the capability, and that will give you an ambiguous relation to the allocations. And this will be how you can do the provenance without additional field. There are a couple of other features of PNVA IODI. It's user disambiguation and exposure tracking parts, which are not relevant in CHERI C, and it allowed us to simplify memory model and streamline a lot of it because they're not relevant. Now talking about proofs. Memory in CHERI could only be accessed via capabilities, so you need the capability to access memory. And in memory model, all the capabilities are stored also in the memory. So that means if you define a predicate on the memory state, it could describe the set of memory regions potentially accessible to the program because it have all the capabilities and all the memory it could access. And we express temporal safety guarantee as a memory state invariance that hold for any sequence of memory model invocation. And we defined three following invariants. The base invariants always hold, it doesn't restrict memory access. The dirty invariants hold between revocation sweeps and permit access only to live or quarantine memory regions. And the clean invariant permits access only to live memory regions. On the right, you can see the hierarchy of memory regions they give access to. Let's look a little bit on the invariants. This is a base invariant. I don't encourage you to try to read the math on the left. It's mostly for illustration. What it says, what it encodes, is the following guarantees: that allocations do not overlap, all allocations fit within the address space, all capability data in CapMap are pointer-aligned addresses, and next alloc ID and last address are indeed low and high watermark. So it's basically a sanity check, consistency check of the memory state. So it doesn't enforce anything, just makes sure it's reasonable, like allocations do not overlap, obviously. So the next more interesting variant is the dirty memory invariant. So it extends the base one with just one clause. And this clause, it states that for all addresses with a valid tag in CapMap, there should be corresponding byte region that decodes its capability, and there must be an allocation, live or quarantined, that includes the lower bound of this capability. Same could be expressed as a security property. Any tagged capability in memory allows access only within the bounds of live or quarantine allocation. The next invariant is a clean in-memory invariant. It extends the dirty invariant with just one additional clause, which states that all allocations are live, by stating that quarantine flag for the allocation have to be false. this is so because when we run the revocation sweep, we discard the data allocations after they have been processed by sweep. We remove them from the quarantine as soon as the pointers to them are revoked. So the allocation map only contains live and quarantine allocation. So a security property, that means any tagged capability in memory allows access only within the bounds of live allocations. So we have proven in Coq that our memory models preserve the clean invariant, the strictest invariant we defined. How we done it, all the stateful operations in our memory model are defined in mem monad, which is combined state and error monads. And the high-level proof statement are expressed with the help of the logic type class, preserves invariant. I didn't include the full definition here, but the definition says that if we start from the state which satisfies the invariant, the result of stateful operation will either be an error or will result in the state satisfying the invariant. We have proven 36 instances of preserved invariant for high-level operations of the memory model, as well for many auxiliary functions. To aid proof automation, we developed a monadic reasoning framework. More about this in the paper. So to summarize, we developed a CHERI C memory model equipped with a sweeping revocation mechanism and the new PNVI CHERI provenance tracking scheme. For our model, we have proven the absence of use after reallocate in all memory states and the prevention of use after free in the clean state. The code of our development is reasonable. The memory model itself about 3,400 lines of code with about 4,000 of auxiliary functions, and the proof is 9,500 lines of code. If you want, I encourage you to read the paper, the CHERI C memory model for verified temporal safety presented here. Another relevant paper you might want to look at is formal mechanized semantics of CHERI C from last year as plus, which discuss a little bit more subtle details about differences between CHERI C and ISO C. We talked mostly about capabilities and pointers, but there are some more subtle details like pointer equality and stuff like that. So if you're interested in these details, that's the second paper. If you want to try our semantics, the easiest way is Docker image. So there are two Docker images we have. The first one allows you to run the command lines executable semantics, which is just, you can run small programs and it will give you after either elaboration or it tell you about undefined behavior or execute them. And there's also compiler explorer-based web interface, another Docker container. The semantics is open source. It's on GitHub, Project Cerberus. The suite is also. My contact information is below, and I'll be glad to answer any questions. Thank you.
Thank you very much. Thank you so much. Are there some questions? Anyone?
Perhaps a naive one. So can you explain whether there is a difference what the sweep operation does and a classical garbage collector would do? Are these in principle two names of the same thing, or?
They are similar in the way. So in C language, in general, garbage collector is not part of the standard language, although you can implement it in it. But I think the main difference between the sweep and the garbage collector in general is sweep not just release this memory to the allocator to be reused, it also makes sure there is no pointers left to it. So I think that would be although you theoretically can implement garbage collector, which also revokes, I guess.
The question over there. Yeah.
So you mentioned there were these. Yeah, you mentioned that there were these four categories of like use after free and use after revocation, and one of them was allowed. Could you say a little bit more about what, like the thing that wasn't caught?
Yes, I think this diagram on the right is the best illustration to that. Oh, we already know. Okay, so we have live objects, and all invariants allow you to access live objects because you need that to your program to work. The difference between use after free and use after revoke is the dirty invariant allows you to access objects in quarantine, and that's use after free. So implication here, the security implication here, you might able to read some data in the quarantine if you somehow manage to get a pointer to it. So it's not terrible. On the other hand, use after revoke, if you have a pointer to the object, it's have been freed, and then the new object was allocated in the same space, and you still have the pointer to that space, you can go there and read the new object, the data you're not supposed to have access at all. So that's a different security implication. So I think that's the difference. Mm-hmm.
Yeah.
Thanks. So since the revocation sweeps are certainly expensive, maybe they will be unacceptable for some environments. Did you investigate formalization of a system without the temporal safety, but just with the spatial safety?
Yes. So we haven't formulated the formal properties of the of spatial safety, but they will be very easy to express on our memory model, because each capability gives you access only to the bounds which is allowed to. So yes. And one thing I haven't mentioned about the sweeps, there are some very smart hardware mechanisms which make them faster in CHERI. So they mark the pages as dirty, so they run sweeps only for the dirty pages, and there are some other like barriers. It's more on the kind of hardware side I'm not too qualified to talk about, but they're not too bad from performance point of view.
Maybe I can also ask a question. So you said you had these 36 instances of the type class. I was wondering about the relationship to your memory model and to the sort of instructions of the machine. Does that mean also that any program that you have?
So these are methods of the memory model. So in memory model, you have method allocate objects, so you have method write to the memory. And there's 36 methods like that, so for each of them we proved this invariant.
I see, thanks. All right, let's thank Vadim again.
Thank you.